Hey everybody, welcome back to part 5 in the Math 215 workbook. We're going to look at a topic here called probability. We're just going to do a very brief introduction of probability. It's a big subject in mathematics, and it's a big part of statistics actually. So this is just is a very, very brief introduction to probability. The word probability is a word that everybody, I think, has some sort of feeling about what it means. And I'm not here to tell you that there's one meaning of probability in general, but in mathematics, probability has a very specific definition. And in order to get problems right that involve probability in mathematics, we have to really understand what is meant specifically by probability in mathematics. So for us here, probability measures the likelihood of an outcome of some random process. Now, what we mean by a random process, a process is random if its outcome is uncertain. That just means that you cannot predict what's going to happen. All right, so that's what we mean by a random process. So for example, when we flip a coin, you cannot predict whether the outcome will be heads or tails. But if you flip a coin over and over again, many, many times, what you will find is that you're going to get heads about 50% of the time and tails about 50% of the time. And so roughly speaking, that's what we mean by the probability. All right, so given some random process, the probability of an event, for example, coin flip comes up heads, the probability of a cancer patient surviving for more than 5 years, could be the probability that a poker hand contains all hearts. All these things we could call events. The probability of those events is the long run frequency or proportion, maybe comma here, of times this event would occur if the process were repeated many, many times. All right, so this is what we mean by probability here. And so the probability of an event is the long run frequency or proportion of times an event occurs. Probabilities are always between 0 and 1. Because they are some sort of proportion, when proportions are always between 0 and 1. So we're only going to really look at the case here of equally likely outcomes. So what we mean by that, like a fair coin flip, right? That represents an equally likely outcome between heads and tails. Another example, rolling a 6-sided die. There are 6 outcomes, but they are all equally likely. Or you could think of something like putting all students' names in a hat, drawing one person's name to maybe answer a question or solve a problem. Everyone is equally likely in the class to be chosen if everybody has their name on a slip of paper in the hat. So that's what we mean by equally likely outcomes. So for any single outcome, the probability of that event, that's what I mean by it here, the probability of it occurring in such a random process is just 1 over n, where n is the number of possible outcomes. When the outcomes are equally likely, we can easily find the probability of any event as a proportion, period. So, for example, there are 2 outcomes when you flip a coin, heads or tails. So the probability of getting a head is 1 over 2. If you're rolling a die, 6-sided die, there are 6 possible outcomes, so the probability of getting any single number is 1 over 6. So that's what's meant in this sentence here. Here's a more general formula that when probabilities when outcomes are equally likely can be computed like this. We use this notation. The probability of the event that you're talking about is computed by the number of outcomes in the event that you're looking at out of the total number of possible outcomes. So here's an example of that notation. P of A is shorthand for the probability of an event A. So for example, when flipping a fair coin, the probability of the event of heads is 1 over 2. All right, so here is example number 1. Suppose we start with a standard deck of 52 playing cards. Each card shows 1 of 4 suits: spades, hearts, diamonds, and clubs, and 1 of the 13 denominations: ace, 2, 3, 4, 5, 6, all the way up to 10, and then what we call the face cards, jack, queen, and king. So that's how you get 52 cards. 13 denominations, 4 suits. 13 times 4 is 52. All right, so we're going to shuffle the cards and draw one at random. What is the probability that the card is, first, a heart? What is the probability that the card is, and then we have 4 examples here. So I want you to pause and try. Use that formula above in the box. Try to apply that to each one of these questions, and then press play when you are done. All right, so let's take a look at these. What is the probability of drawing a heart? Well, the number of outcomes in this event. So what are the number of, how many, it's basically asking for how many hearts are there in the deck. Well, there are 13 hearts. How do I know this? Well, for these denominations, ace through king, we think of the ace of hearts, the 2 of hearts, the 3 of hearts, the 4 of hearts, all the way to the king of hearts. And that's all the hearts. So there are 13 of them. Out of how many cards are there? Well, there's 52. This reduces to 1 over 4. You could also compute it as a decimal or as a percentage. Those are all the same number. So there's a 1 in 4 chance of drawing a heart. One way of looking at it, there's 4 suits, right? And hearts are one of those suits. So that's another way of viewing this as 25%. What's the probability that you draw a jack? Well, how many jacks are there in the deck? Well, there's a jack of spades, a jack of hearts, a jack of diamonds, or a jack of clubs. So there are 4 of those, and still out of 52 cards. This reduces to 1 out of 13, which if you put in your calculator is about 0.77 or about 7%, 7.7%. What's the probability that you get a jack of hearts? Well, there's only 1 jack of hearts in the deck. Right, so this is a 1 in 52 chance. If you put this in your calculator, that's approximately 1.9% or 0.019. All right, now what's the probability that we have a face card of any suit? Well, we just have to think about how many face cards there are, right? Well, there's a jack, queen, and king, but for every suit. So there's 3 face cards for every suit. That's 3 times 4. It's 12 out of 52. 12 out of 52 reduces to 3 over 13, which in your calculator is approximately 23%. All right, so this is what we mean by a probability. A probability of an event is how many times that event you're looking at can occur out of the total number of possible outcomes. All right, so taking this a little further, we're going to look at calculating the probability of a combination of events. So outcomes and events can be combined in various ways to form new events. For example, we might be interested in the probability that 2 events are occurring at the same time, or at least one of the 2 events occurs, meaning one of the things or both of the things could occur. We might want to know the probability that an event does not occur, or that one of the events occurs if the other occurs. There's lots of different ways, lots of different things we might be interested in. So here we have a second example. It's based on this data here, that the United States Senate consists of 2 senators for each of the 50 states. That's why we have 100 senators. The table below shows the breakdown by party affiliation and the gender of the 100 senators who were in office in 2016 on the 1st of January. So if you were to select one senator at random from the U.S. Senate, what is the probability that the senator is one of these things from 1 to F? So I want you to try that, still using the same concept of probability, the same conception from the previous page. So see if you can apply that to this problem here, and then press play when you are done. All right, so let's take a look at these here. What is the probability, if we choose a senator at random, that that senator is a woman? I see there's 20 women out of 100, right? So our probability of a woman being chosen, there are 20 possible women out of 100 possible senators. So that's a 0.2 probability. Right here, I'm going to start sticking to decimals as probabilities because that's the most common way that we express them. Now, what's the probability that that senator would be a Republican? Well, how many Republicans do we see? I see 54. All right, so this will be 54 out of 100, which is a 0.54 probability. Okay, now what about a Republican woman? Well, there are 6 of those, right? There are 6 senators who are both women and Republicans. So that is 6 out of 100. So that means you're a woman and a Republican, not or. 6 out of 100. So that's 0.06. So it's a very small probability that we would choose a Republican woman if we chose at random from all senators. Now, what about this one? The probability of being a woman given that they are a Republican. We're going to learn pretty soon there's a notation where we can write this much more shortly. But for now, I'm just going to write it out just to be clear. All right, so if it says given, if it says a woman given that they are Republican, that means we're only going to focus on this column. So given that one's a Republican already, there's only 54 of those. So that's going to be our denominator. And then within that column, there are 6 women. That's our fraction. And this is approximately, this is 1 over 9, which is 0.1 repeating. So it's about 11%. Now, but what about this one? So this is just a little bit different language, but it applies kind of a similar idea to this, but it's switching it around here. What's the probability that we choose a Republican given that the senator is a woman? Part D is probability of woman given that they are Republican. This problem's probability of a Republican given they're women. So here we're only considering all the women. So there are 20 total female senators. Of that, there are 6 Republicans. So here we have 3 of 10, which is 0.3. So these probabilities sound similar when we're saying probability of a woman, choosing a woman given they're a Republican, probability of a Republican given that they are a woman, sounds similar, but it's a different question, right? It's a different group that you're looking at. In the first, you're only looking at Republicans, seeing how many women there are in that group. Part E, you're looking at how many women there are, and in that group, how many of those are Republicans. Now, how about this one? The probability of being a woman or a Republican. I'm not going to write the wording or both because in mathematics or statistics or logic, when you say A or B, it means A or B or both. So you have to kind of get used to that because that's not really how, when people use or in everyday speech, that's not what they mean. So like if someone says, hey, I'm going to the market to get a sandwich, would you like a turkey sandwich or a veggie sandwich? They're not asking you, would you like a turkey or a veggie or both? But in math, we would assume that that means a turkey sandwich or a veggie sandwich or both. And there's a special way to say that you don't mean that. It's called the exclusive or. So unless someone says it's the exclusive or, specifically is telling you that it's the exclusive or, you assume the word or means A or B or both. So that's written out here explicitly in part F, but if you ever come across this in math, keep in mind that if it's both, it also qualifies as or. All right. How do we think about this? Well, the same way that we think about all of them. What's the total number that we're choosing from here? So here we're not restricting to being a female or being a Republican. We're looking at the 100 as the total again. Now the tricky part is how many people are women or Republicans? How do we do that? We can add how many women we have, which is 20. So that's how many women, plus how many are Republicans, right? Which is 54. But there's a trick here. There's something we have to keep in mind. That some of the senators are both women and Republicans. So we need to subtract those people who are both, because otherwise you're counting them twice, right? There are 6 women who are both Republicans and women. So I have to subtract that number to get 68 out of 100, right? Because if I was to call that 74, I would be counting 6 of those women twice, once as women and once as Republicans. We only want to count each one once. All right, so I'm going to cut the video here. We'll do a short video on conditional probability in the second video. See you there.